When we talk about artificial intelligence, there's this massive, almost universal blind spot in how we tend to think about it.
Oh, absolutely. We completely obsess over the brain.
Right. We treat these large language models like giant disembodied brains floating in a jar.
Yeah, we just endlessly debate their parameter counts or, their training data.
Exactly. The neural weights, as if the raw, innate intelligence of the model is literally the only thing that matters in the real world.
It really is the prevailing narrative right now. We treat the model itself as if it were the entire software system.
Yeah.
But the reality of deploying AI is that the model is just one piece of a much larger puzzle. It's
Yeah.
not even close to the whole picture.
It's really not. And well, that brings us directly to the mission for today's deep dive. We are looking at a stack of incredibly fresh research today.
Super fresh.
Yeah, primarily driven by a groundbreaking new paper from researchers at Stanford, K-Rafton, and MIT. It's titled Meta Harness, End-to-End Optimization of Model Harnesses. And what this paper proves is that you can have the smartest, most capable AI brain in the world, but if you put it in a messy, chaotic workspace, it is going to perform terribly.
Completely tank.
So today, we are exploring that workspace.
And, the technical term for that workspace is the harness. To give everyone a sense of the stakes right out of the gate, changing this invisible code, just altering the workspace around a fixed AI model without changing the model itself, it can swing its performance on a benchmark by a factor of 6.
Wait, a 6 times performance gap?
Yeah, a factor of 6.
That is unbelievable. I mean, a leap like that completely shifts where we should be focusing our engineering efforts.
That's staggering, really.
Exactly. So whether you are a developer actively building these systems or, you're just someone who is endlessly curious about the absolute frontier of technology, this fundamentally shifts how you should understand AI capability.
Because today, we're going to look at how researchers have figured out a way to let an AI autonomously build and perfectly optimize its own work environment.
Right. It's no longer just a static calculator answering prompts. It is acting like a brilliant software detective.
Learning from its own past mistakes.
Exactly. Building a better version of itself.
Which is a crucial evolution. Because until this paper, building these harnesses has been this frustratingly human bottleneck.
So before we get into the exact mechanics of how this meta harness system actually works, we really need to ground this. We need to understand what a harness actually is under the hood.
Yeah, and why human engineers are currently so terrible at building them.
That's the perfect place to start. So fundamentally, a harness is the external code that wraps around a language model.
Right. It determines exactly what information to store in memory, what to retrieve from external databases, and precisely how to format and present that information to the model at any given step.
It is the orchestration layer that actually connects the AI to the task. Okay, let me try out a metaphor here.
Go for it.
Imagine the large language model is a brilliant, highly capable corporate executive. But this executive has a profound total case of amnesia.
Oh, I see where you're going with this.
Every time they blink, they forget what meeting they're in, what company they work for, everything. The harness, then, is their executive assistant.
I love that. That's exactly how it functions.
So this assistant is the one constantly deciding what goes into the permanent filing cabinet, what gets quickly jotted on a sticky note and slapped on the monitor, and, what gets placed directly on the desk in front of the amnesiac executive right this very second so they can make a decision.
Right, because if the assistant hands the executive a totally irrelevant file, the executive makes a terrible, uninformed decision.
And right now, human developers are the ones desperately trying to train that assistant.
Yeah, and harness engineering is currently a heavily manual, intensely tedious process.
Just trial and error, basically.
Exactly. Human engineers sit at their desks, inspecting failed AI outputs, tweaking retrieval heuristics, adjusting prompt templates, and basically just guessing what went wrong so they can try again.
But wait, let me make sure I'm following the timeline of AI development here. I know we have tools like OPRO or TextGrad systems that basically use one AI to automatically tweak and improve the text prompts for another AI.
Right. Those have been around for a bit.
So if we already have those existing AI optimizers, why can't we just point them at the harness and let them fix the assistant?
It's a great question, but those prior optimizers fail spectacularly in this specific setting. What's fascinating here is the reason comes down to how they handle feedback.
How so?
They heavily, almost violently compress the feedback before they give it to the AI.
Compress it like a zip file.
More like a terrible summary.
Yeah.
Most of these older optimizers are essentially memoryless.
Oh,
They might only look at the very last attempt the AI made. Or worse, they just give the AI a scalar score like a number out of 100, or a tiny one-paragraph summary of what went wrong.
wow, that's not helpful at all.
No. If you've ever tried to debug a complex piece of code by just staring at an error 404 message or a piece of paper that says grade F, you know exactly why the AI was failing. It doesn't tell you why it failed.
Ah, I see. Because in a harness, the failure might have happened way earlier.
Exactly.
Like the assistant pulled the wrong file from the cabinet at 9:00 a.m., but the executive didn't make the catastrophic business mistake until 3:00 p.m.
Right.
A tiny text summary saying you failed at 3:00 p.m. cannot capture that long horizon causality.
Precisely. A single bad choice in document retrieval can cause the AI to hallucinate or fail 50 reasoning steps later.
Okay, let's unpack this. Because if compressed summaries are the problem, how do you actually give the AI the full, uncompressed picture?
Well, that's the real challenge.
Because if you just try to stuff 50 previous massive attempts into a single prompt, you're going to completely blow up the AI's context window, right? You can't just shove infinite data into a prompt.
No, the model would just crash or lose track of everything.
Right. And that constraint leads us directly to the core innovation of MetaHarness. It is an outer loop system that uses a highly advanced coding agent. Specifically, they used Claude Code running the Opus 4.6 model as the proposer.
And the brilliant architectural choice the researchers made here is fundamentally about changing how the AI accesses its own history.
Okay.
Instead of trying to stuff all that feedback into a single massive prompt, MetaHarness gives the proposing agent full, unrestricted file system access to its entire past.
File system access. So to stick with our metaphor, instead of the assistant trying to memorize what happened yesterday, we are giving the assistant the keys to the company's massive sub-basement archives.
Exactly. They can just walk down there and look at every single memo they ever handed the boss.
That is
The
wild.
system automatically creates a new directory on the hard drive for every single candidate harness it evaluates. The file system stores the source code of every prior attempt, the evaluation scores, and, most importantly, the raw, completely uncompressed execution traces.
And when you look at the scale of this in the paper, it is genuinely hard to wrap your head around. The researchers note that a single evaluation can produce up to 10 million tokens of diagnostic information.
It's massive.
Just to visualize that, for you listening, 10 million tokens is roughly equivalent to reading the entire Harry Potter book series 10 times over.
Yeah, there is no context window on Earth that can process 10 million tokens of dense, step-by-step software logs effectively in one single prompt.
Which is exactly why the agent navigates it exactly like a human software developer would. It uses standard terminal tool.
Right. It uses the grep command to search for specific error codes buried deep across old logs. It uses the cat command to open and read specific
Yeah,
files.
it's just browsing the file.
Yeah, and the researchers track this behavior. The proposer agent reads a median of 82 separate files per iteration.
Wow. 82 files.
About 40% of its time is spent looking at old source code, and another 40% is spent poring over those raw execution traces to see exactly where things went off the rails.
It is literally acting like a senior developer hunting down a bug.
If we connect this to the bigger picture, we are moving away from packing context, just shoving everything into the prompt and crossing our fingers, to what they call adaptive access.
Right, the AI decides what it needs to see. But, it's one thing to say an agent can read a file system. It's another thing entirely to see what it actually does with that power.
Oh, absolutely. The theory is one thing, the practice is another.
Here's where it gets really interesting. The paper gives us a qualitative look at the agent's causal reasoning, and it reads like a tech thriller. They tested this on a brutal coding benchmark called Terminal Bench 2.
Oh yeah, Terminal Bench 2 is notorious in the AI engineering space.
It really is.
It evaluates agents on long-horizon command line tasks. Imagine you tell an AI, go set up a secure functional web server from scratch in this Linux environment.
So tasks where one wrong terminal command early on destroys the whole run.
Exactly, it's unforgiving.
So they set MetaHarness loose on this exact problem. And the search log, which is basically the internal monologue of the AI trying to build a better harness for itself, is fascinating.
What did it do first?
Well, for the first 6 iterations, the agent kept trying to fix these deep structural bugs in its own code. For instance, the AI was getting trapped in infinite verification loops.
Right, where the agent would successfully solve the task, But then it would get overly paranoid and burn 40 extra steps checking if a file existed over and over again because of a flawed control loop in the harness.
Exactly. And another bug was terminal markers leaking. Basically, weird system code characters were accidentally bleeding into the text prompt and confusing the model.
Classic formatting error.
Yeah, so the proposing agent tries to write code to fix these structural bugs. But at the exact same time, it also decides to start tweaking the comps in the
Oh,
harness.
changing two things at once.
Right, it tries to add new cleanup directives to the instructions. And the results of doing both at once, terrible. For 6 iterations, the performance just tanks. It keeps getting worse.
Now, if this were a traditional text optimizer, it would just see those failing overall scores and probably abandon the structural bug fixes entirely.
Because it wouldn't know which part was broken.
Right. It would just see grade F. But because MetaHarness has access to the raw execution traces in that sub-basement archive, we get this incredible moment of clarity.
Yes. The agent goes down to the archive, looks at the actual step-by-step logs, and realizes, wait a minute, the structural fixes I wrote to stop the loops are actually totally fine.
They were working.
They were working, but they're being confounded by the prompt changes. The new cleanup prompts were making the model delete necessary state files before the overall task was actually complete.
That is amazing. The agent explicitly deduced causality. It realized I changed two variables. Variable A is good, but variable B is toxic.
So it hits iteration 7 and it pivots completely. It explicitly decides to stop touching that fragile control loop entirely.
A smart move.
Yeah, instead it invents something purely additive. It builds what it called an environment bootstrap.
And the elegance of the environment bootstrap is brilliant. The agent wrote a single compound shell command that runs before the language model even starts its main loop.
Just checking the environment.
Exactly. It quietly grabs the current working directory, checks what programming languages are installed, like Python or Rust, and checks for active package managers.
So it essentially takes a snapshot of the digital room and hands it to the AI on turn 1.
It literally just maps the room and turns the lights on before the amnesiac executive even walks through the door.
And the reason that works so well is deeply tied to the domain of coding, right?
Absolutely. In a complex, unknown terminal environment, a standard AI will typically waste its first 2 to 4 turns just blindly exploring.
Like, do I have Python? Let me check. No. Do I have GCC? Let me check.
Right. By bootstrapping that snapshot, it completely saved those wasted exploratory turns. It allowed the AI to jump straight to actually solving the problem.
The results of that simple logical addition are undeniable. This autonomously discovered harness beat the absolute state-of-the-art hand-engineered system, which is called Terminus Cura.
And just for context, Terminus Curi is a massive system built by human experts over months of trial and error.
And MetaHarness beat it. Using the Claude Haiku 4.5 model, it ranked #1 among all tested agents. It quite literally beat human engineers at designing a workspace for itself.
It's the perfect example of why giving the AI access to the raw execution trace matters. It needed to see exactly why the early iterations failed to realize it needed an additive snapshot solution, rather than trying to subtract code from the control loop.
But of course, as impressive as that is, Terminal Bench 2 is just coding. Terminal commands are very structured, very logical.
True.
If this is truly a breakthrough in how we build AI, it shouldn't just work for command line tasks. So what happens when you throw something highly abstract at it?
Like math.
Yes. Let's talk about how MetaHarness reshaped completely different domains, starting with high-level math.
Mathematical reasoning is a fantastic test case because it's a domain where, historically, naive information retrieval actually hurts AI performance.
Right. If you give an AI a complex calculus problem and your harness assistant just automatically searches a database and dumps the 5 most mathematically similar texts onto the executive's desk, it usually just confuses the model.
It brings in irrelevant formulas or overlapping proofs that muddy the waters.
You clearly need a highly custom strategy.
You do. So, what did MetaHarness do when faced with this? Without any human intervention or hints, it autonomously went into the code and invented a 4-route BM25 highway.
Okay, for anyone who might not be deep in the weeds on search infrastructure, BM25 is essentially a classic search engine algorithm. It looks at keyword frequency to rank how relevant a document is to a query.
Exactly.
So it built a 4-lane highway using that search algorithm.
Yeah, it built a system that first looks at the incoming math problem and categorizes it. And it learned that different types of maths require completely different retrieval strategies.
Give me an example.
Well, if it detects a combinatorics problem, it fetches 20 examples from the database, aggressively deduplicates them down to 8, re-ranks them by difficulty, and only keeps the top 3.
Mechanistically, it learned that for combinatorics, the AI needs a high diversity of examples because combinatorics logic branches out in so many different ways.
But it still needs hard matches.
That makes total sense. But then for geometry, it does something entirely different.
Right. For geometry, it decided to always pull one fixed, highly difficult reference example plus 2 raw keyword matches with absolutely no re-ranking at all.
Wait, really? Why would it do that?
Because geometry problems often share very rigid structural setups. You don't need diverse branching logic. You need a rock-solid structural template.
Oh, I see.
So it builds separate, custom logic for geometry, another one for number theory, and a default route for algebra.
It essentially built its own highly specialized, multi-stage search engine just for mathematical reasoning.
And the result of that custom highway, without changing the underlying model at all, this discovered harness improved accuracy on 200 incredibly difficult international mathematical Olympiad-level problems by an average of 4.7 points.
That is a huge jump.
But the detail that actually changes the game here, it achieved that 4.7-point jump across 5 completely held-out models.
Wait, models it wasn't even trained on?
That is the crucial takeaway. The harness was discovered using one specific model during the training phase. But when the researchers took that exact same harness code and applied it to 5 other models that the system had never seen before.
Including models built by completely different companies.
Yes, the 4.7-point improvement held up across the board.
So it didn't just learn a weird quirk of one specific AI. It discovered a fundamental, universal truth about how to structure mathematical context for machine learning models.
Precisely. The logic transferred universally.
Okay, but let me throw a hypothesis at you regarding their final test, which was on text classification. This is categorizing messy human text like sorting legal documents for fraud or categorizing medical symptoms.
Right.
When I hear that the AI is building its own context, my immediate thought is that the winning harness must just be a massive context dump, right?
You'd think so.
Is it just shoving as many examples of fraud into the prompt as possible until the model brute forces the right answer?
It is a completely logical assumption, especially given how huge context windows are getting, but no. In fact, the AI discovered that the optimal path was the exact opposite.
Really?
On the text classification benchmarks, MetaHarness achieved a massive 7.7-point increase over the state-of-the-art hand-designed system, which is an architecture called ACE.
Okay.
But it achieved that jump in accuracy while using 4 times fewer context tokens than ACE.
Wait, 4 times fewer tokens? Is it just ruthlessly cutting out the noise so the model doesn't get distracted? How does using less context make it almost 8 points more accurate?
It comes down to a structure the researchers call a label-primed query harness. Instead of just dumping dozens of examples onto the executive's desk, the agent wrote a highly structured surgical program.
How does it work?
First, it explicitly shows the model, the entire valid answer space up front. Then, it provides exactly 1 highly relevant coverage example per class.
And then it uses what it calls contrastive pairs, right? When I read this part of the paper, it blew my mind.
The contrastive pairs are genuinely brilliant. The harness actively searches its memory for highly similar examples that have different ultimate labels, and it places them side by side in the prompt.
So to use our metaphor, this is like the assistant realizing the executive always mixes up fraud and accounting error.
Right.
So the assistant purposely puts 2 nearly identical corporate case files side by side on the desk and says, look, this file is fraud, but this file that looks almost identical is just a benign accounting error, and here's the one sentence that makes the difference.
Exactly. It sharpens the decision boundaries locally, exactly where the model is historically most likely to get confused.
Wow.
Let's say you're classifying medical text. It shows the model a patient with a mild cough versus a patient with a mild cough and a slight fever, and clearly demarcates the line between a cold and the flu.
Because it's so targeted and precise, it uses way fewer tokens than a scattershot dump of 50 random medical files.
And it reached this optimal performance incredibly fast. It was 10 times faster than prior text optimizers.
10 times.
Yeah, it only took about 4 iterative evaluations of reading its own logs to match the best existing human-built systems, and then it just blew past them.
Because it's not guessing. It's reading its own trace logs, seeing exactly where it failed to classify a tricky document, and building a specific tool like the contrast of pairs to directly address that exact failure mode.
Exactly.
So what does this all mean? We started this deep dive talking about the massive blind spot in AI, our obsession with the AI brain, and our total neglect of the workspace.
Right, the harness.
Meta Harness proves that the future of artificial intelligence isn't just about throwing billions of dollars and megawatts of power at training marginally bigger models.
No, it's about tooling.
The real frontier is models that use full, uncompressed diagnostic histories to act as their own structural engineers. They are building hyper-efficient, custom-tailored environments for themselves that human developers would simply never have the patience or, frankly, the granular insight to hand code.
It represents a profound shift in agency.
Yeah.
In the space of a few short years, we've gone from AI as a static tool we operate to AI as the active engineer of its own tooling.
Yeah, it's a huge shift.
And this raises an important question, something for you listening to really mull over after we wrap up today. This paper clearly shows that when AI has access to its full history, it builds incredibly efficient, highly logical, and sometimes deeply counterintuitive tools to interface with raw data.
Like the math highway or the contrastive pairs.
Exactly. It knows what it needs to succeed better than we do.
Right, it knows its own mind.
So, if AI is now perfectly capable of autonomously designing the optimal interfaces it uses to interact with the digital world, I mean, how long until it starts redesigning the interfaces we use to interact with it?
Oh, wow.
If it knows exactly how it best receives and processes information, it might just realize that a simple blank chat box is a terrible, highly inefficient bottleneck for human-AI collaboration.
That is a wild thought. From optimizing the AI's workspace to optimizing our workspace, that amnesiac executive might just decide to fire the assistant and build a whole new office building from scratch.
It just might.
Thank you so much for joining us on this deep dive into the Meta Harness paper. It has been an absolute blast unpacking this with you.
Thanks for having me.
Until next time, keep exploring the frontier.